Comparative analysis of dry type and oil-immersed transformers. Engineering first point is thermal management methodologies. Dry type transformer employs convective airflow, either natural AN or forced AF, to facilitate thermal dissipation. While this method is inherently less thermally efficient, it enhances operational safety by eliminating liquid dielectric media. Oil-immersed transformer utilizes dielectric liquids, typically mineral or synthetic oil, that convectively and conductively absorb thermal energy, subsequently dissipating it through radiators or heat exchangers. This affords superior thermal performance under high load conditions. 2. Structural design attributes. Dry type. Windings are embedded in epoxy resin or other thermosetting compounds under vacuum pressure impregnation, VPI, ensuring mechanical integrity, moisture resistance, and reduced partial discharge susceptibility. Oil type comprises windings fully immersed in insulating oil within a hermetically sealed tank. The structure typically includes conservators, breather systems, and thermal expansion mechanisms. 3 maintenance regimens. Dry type, characterized by minimal servicing requirements limited to periodic inspections and removal of surface contaminants. No oil diagnostics are necessary. Oil type necessitates comprehensive routine diagnostics, including dielectric strength testing, dissolved gas analysis, DGA, moisture quantification, and oil purification protocols. Fourth, deployment environment. Dry type, optimally suited for enclosed environments with strict fire safety requirements, such as healthcare facilities, underground substations, and high-rise infrastructure. Oil type, primarily deployed in outdoor or high-capacity utility substations, where ventilation and fire containment infrastructure are integral. 5. Combustibility risk. Profile dry type, intrinsically fire retardant due to absence of flammable fluids, rendering it compliant with stringent fire codes. Oil type, presents heightened fire hazards, requires additional mitigation strategies such as bund walls, nitrogen inerting, and flame arresters. 6. Energy efficiency and volumetric considerations. Dry type, lower efficiency and increased physical footprint stem from less effective heat dissipation and reliance on solid insulation. Oil type achieves higher thermal efficiency, enabling smaller core sizes and optimized magnetic flux distribution. 7. Economic trade-offs. Dry type exhibits higher capital expenditure due to advanced insulation systems and manufacturing processes. Operating expenditures, however, are comparatively modest. Oil type, lower initial procurement costs but subject to higher total cost of ownership due to maintenance, fire safety, and environmental compliance. 8. Functional applications. Dry type, ideal for safety critical installations such as mass transit systems, nuclear facilities, marine vessels, and environmentally regulated zones. Oil type, preferred in grid level transmission, renewable energy integration, and heavy industrial processes demanding high power densities. 9. Environmental sustainability metrics. Dry type exhibits minimal ecological footprint. Absence of fluid media mitigates risk of soil and groundwater contamination. Oil type requires adherence to environmental impact mitigation measures, including containment pits, oil recycling, and hazardous waste disposal. 10. Acoustic emissions. Dry type typically exhibits reduced noise levels due to resin damping of core vibrations, suitable for installations near occupied spaces. Oil type may generate elevated sound pressure levels from magnetostriction and fluid dynamics. Noise attenuation measures are frequently necessary. 11th, thermal overload response. Dry type, limited thermal headroom under overload conditions, susceptible to rapid degradation of solid insulation. Oil type, superior thermal inertia, facilitates temporary overload tolerance, preserving insulation longevity. 12th, hygroscopic performance. Dry type, high resilience to ambient humidity, enabling deployment in coastal or high humidity environments without auxiliary protection. Oil type, susceptible to moisture ingress, adversely affecting oil dielectric properties and potentially inducing dielectric breakdown. 13th, dielectric architecture. Dry type utilizes high temperature class insulation systems, class FH, including epoxy resin, aramid paper, and fiberglass compositors. Oil type relies on a combination of dielectric fluids and cellulose-based solid insulation for fuel management and heat dispersion. 14. Diagnostic instrumentation, dry type, offers limited condition monitoring, typically restricted to thermal sensors and manual visual inspection protocols. Oil type supports advanced online diagnostics, including Buchholz relays, DGA, thermocouples, and real-time SCADA integration. 15th, operational lifespan, dry type, average service life ranges between 20 to 30 years under nominal operating conditions. Derating may be necessary for extended longevity. Oil type, life cycle often exceeds 40 years, with robust preventative maintenance, preferred in long duration infrastructure planning. 16. Mechanical resilience, dry type, enhanced structural rigidity and seismic tolerance due to solid encapsulation, suitable for mobile and offshore installations. Oil type requires mechanical dampening supports in seismic prone areas due to more flexible construction. 17. Thermal management typologies, dry type, employs either AN or AF modes, may include thermostatically controlled fans for dynamic thermal response. Oil type classifications include O, N, AN, ON, AF, OFAF, and OFWF, allowing scalability and thermal capacity through forced convection systems. 18. Regulatory and code compliance, dry type, fully compliant with IEC 6076-11 and NFPA standards governing indoor electrical installations and fire resistance. Oil type must meet comprehensive environmental and safety regulations, including EPA spill containment and IEC C57 standards. 19. Retrofit and serviceability. Dry type, typically considered non-repairable post-installation failure. Upgrades are limited and often economically unfeasible. Oil type, modular design permits component-level servicing, including tap changer, replacement, and oil rejuvenation. 20. Logistical considerations, dry type, transported without fluid containment measures, lower risk during transit, and easier installation footprint. Oil type requires rigid transport protocols to prevent leakage, oxidation, or mechanical displacement of internals. Extended comparison summary table. The extended comparison summary table provides a clear, organized view of key differences and similarities between various items. It delivers concise yet meaningful insights, enabling readers to evaluate multiple options side by side with ease. By highlighting strengths, weaknesses, and shared characteristics, this format simplifies the analysis process. Its structured design supports faster, more precise, and well-informed decision-making across a wide range of scenarios. Thank you for watching. For more updates, please like, share, subscribe my YouTube channel, BrainToonPro, and follow my Facebook page, Creative Master. Thank you.